All right. So the reason this is a great little break between Unit 1 and Unit 2 is Unit 1 is meant to give you all the foundation of calculus, the visual and graphical foundation of where, how these derivatives come from, what they are, how they're first initially found. So they're first initially found graphically, then they're found from yesterday's formula called first principles. But then as people started using first principles and doing all the graphing, they started to notice patterns. And these patterns happen quite a bit and will allow us and save us some time to be able to discover the things that we're working on. So all of these different patterns and recognitions of what we have is put together into a collection or a unit called differentiation. Okay, differentiation is the verb on finding a derivative, which is the noun. The noun is the derivative. The verb is differentiation. So in being able to differentiate is the action of finding the derivative. And we use these by a system of tools and rules. There are 5 main, well, 5 lessons, but I think about 11 or 12 different rules that we're going to learn in a day and a half. But each rule or tool is built on the other ones, okay? And the first one you discovered in that Desmos activity, and I imagine that some of you already discovered it when you were doing the sketching in the first 2 days, and that is the power rule. So I'm going to show you what the power rule is, but in all of these definitions, wait. There we go. So in all these definitions, I'm going to give you the mathematical definition of it, but understanding it with an example is going to be much easier. So if the original function is x to the power of n, so for example, we saw x squared and x cubed, then the derivative is n times x to the n minus 1. This is a fancy way of saying that you take the exponent, bring it down and multiply it by the coefficient, because the exponent is going to tell you how much the derivative has to get stretched, and then take 1 less than that, because we already discovered the derivative is always 1 less than the original. Now that's great, a really great mathematical definition, but an example is better. So if f at x equals x to the 126, then f prime at x equals, can someone tell me?
126x to the power of 125.
Exactly. And just imagine if I had asked you to do this question yesterday. So yesterday, don't write this down. If it was x to the power of 126, we would have to go off and say the limit of x, or h approaching 0 of what was it, f at x plus h minus f at x all over h. Okay, great. Then we would go the limit of h approaches 0. This would be x plus h to the power of 126 minus x to the 126 over h. What's the next step? Expand. Oh, great. We get to expand x plus h, x plus h, x plus h, and we only have 126 more to go. And then you got a rainbow. These two get an answer, rainbow that. You can imagine what would happen. It would just be a nightmare. All right? And then you would rainbow that and all that sort of stuff, get it all down. whole bunch of stuff would cancel, and eventually you get down to 126x to the power of 125. But we don't want to have to use this method to try and tackle a function like this when we can recognize the patterns. The next obvious answer is, why did we learn this in the first place if we could have come up with this pattern all the way along? Well, we need to understand the foundations of what things are doing in order to take the next step, and to understand the first floor before you can go to the second floor. You can't just jump to the second floor without having a first floor and a basement. And for the last 3 days, we've been building the basement, which is the understanding the graphical stuff. We did our first floor yesterday and bringing up the derivative that way from first principles. But now we can build on that basement and that first floor and start to build a high rise. We can build all sorts of good stuff, and we can go really far because we have a strong base. And that's really why we've spent the time investing in it to get to this stage. What you need to know too is, for as early, not too long ago, math wasn't taught using this foundation. The calculus wasn't it. This was my first day of calculus. When I learned calculus, my teacher walked in and said, trust me, the derivative of x to the power of 126 is 126x to the power of 125. Just said, this is the rule, trust me, it works, and that was it. And all I did was memorize rules and not ever understand what was going on. But building that foundation hopefully allows you to understand where these rules are going to come from. And now we'll just start using them. And we're going to use them quite a bit to be able to solve really complicated ones that we wouldn't even want to think to do graphically. Okay? So the investment of time we spent in the last 3 days is going to help with all of these rules. All right, so there's our first rule, the power rule. The second rule is called the constant multiple rule. And again, you actually discovered this rule within that Desmos activity by saying, you know what? Not only is the degree 1 less and it comes out front, but if there's already a coefficient, those two coefficients have to get multiplied together. Okay, so that's actually what this rule says, even though it doesn't look like it. It says, though, that if there is a coefficient, we kind of ignore it for a second, do the derivative of the function, and then bring our answers together. So if we had f of x was 7x squared, I know that I saw in that Desmos activity that you all can predict that the derivative is 14x. I'm going to show you why it's 14x, because the constant multiple rule says this. If there is a coefficient, ignore it for a moment and take the derivative of the function. So pretend it's just x squared, just like the power rule, right? Oops. The power rule doesn't have a coefficient. So we're just going to take the derivative of this using the power rule. And the power rule says the derivative of x squared is 2x. And then we simplify. Forget calculus for a second. We just do some regular algebra and say 7 times 2 is 14. And we get 14x. So the constant multiple rule actually says if there is a coefficient, ignore it and do the derivative of the actual function, and then simplify afterwards. But in reality, none of us do this second line. We all go from here because we can see that that 2 comes down and gets multiplied by the 7 and gets 14x. Okay? So even though this is the rule that allows it to happen, this middle line, we always just sort of put those two together and get this answer. One other thing you'll notice is my notation, and the notation is extremely important. You see that when I take the derivative, I have to have this little part here, okay? And I need to tell the reader that I'm taking the derivative. What I don't want to see is this. Questions like this, where it's 7x squared, so f of x is 7x squared, and the person under says, oh, They just do this. That is wrong. That is not correct. This is not calculus, because 7x squared is not equal to 14x. What is equal to 14x is the derivative. Okay, so you must write this line when you're actually taking the derivative. Okay, now if there's other stuff you do afterwards, it's still equal to f prime at x, but make sure I see this line, f prime at x, when you're taking the derivative. Okay, good. So those are the two rules that you discovered in this morning's Desmos activity. But you actually probably might have discovered some other ones that I will throw in here as well. The next is called the sum rule. And it says if you have a function that is actually the sum of two other functions, you can take the derivative of each function by themselves and then add them together. Now, often we don't see functions or visually imagine that functions are actually a combination of two functions, but they are. Again, think back to the end of advanced functions where we did combinations of functions. We took a quadratic and added it to a line. Okay, we've been doing combinations. And again, this is why it used to be so good that we could just go from one course to another. We would have that connection to what we did last course right here. But we're remembering. So all sorts of functions are actually combinations of functions. So here's an example. This function is clearly a combination of x cubed plus x to the power of 4, a cubic and a quartic. So if we're taking the derivative, the sum rule says that we can take the derivative of the first one and add it to the derivative of the second one. So the derivative of x cubed. Brenna, what's the derivative of x cubed?
Would it be 3x squared?
Very nice. And Delaney, the derivative of x to the power of 4.
4x cubed.
Yes. Can I add these together? Well, no, because they are unlike terms. But I did take the derivative of the first one plus the derivative of the second one. Okay? So there's an example of how the sum rule comes in. Again, imagine the amount of work we saved ourselves instead of having to do what we had to do yesterday, where we had to take the limit and we would have to do x plus h and raise it, multiply it 3 times, and then do it 4 times, and then bring it all together and get those huge long answers just to get down to an answer like this. I'll do a second example. I'll call this g at x, just a different letter for a different function. Doesn't matter what I call it, f or g or h or whatever. At first glance, you might not think that this is a combination of a bunch of different functions, because this looks just like a parabola, like a trigonometry or a trinomial that we learned in grade 10. And it is, but it's actually a quadratic plus a negative line plus a constant. Okay, so let's find the derivative of this. So even though it's called the sum rule, you're allowed to add negatives. So if you have a minus, that's not a big deal. But the derivative of x squared is 2x. What do we think the derivative of negative 4x is?
Negative 2.
Why negative 2?
I don't know, you just more positive 2. You just, or not, I don't know.
Would
Just,
it be negative 4?
yeah, sorry, negative 4.
Okay, I think you meant to say 4 and just said 2. Yeah. Okay, good. Yep, you're right. Bang on. And then what's the derivative of 1? So that's an interesting one. So let's imagine what this is. The function 1 is actually a line like this, y equals 1. What is the slope of that line?
0.
0 all the time. 0. And we kind of saw this happening yesterday. Remember those constants disappeared? Because the slope of a constant is 0. So the derivative of 1 is 0. So we wouldn't add, we could go add in a 0 if we wanted. We'd have that. Okay? But we probably wouldn't write that part down. Good. The 4x, what's the derivative of 4x? Well, this one's negative 4x. So what does negative 4x look like? Well, it kind of looks like this. The slope of that is always the same. And in this case, it's always negative 4. So the derivative of negative 4x is negative 4. Okay, so the sum rule. Good. This we kind of actually just talked about. The derivative of a constant rule. If your function is a constant, then the derivative is 0. So there's y equals 4. Right, f of x equals 4, that's y equals 4. Well, the slope of all of these, all of the tangents, is always 0. So the slope, or the derivative, then is just 0. So we saw that pop up in the last example too. Okay, so let's try and combine a few of these together into some questions. Okay, so the original is 4x squared. Reese, you got an idea of what the derivative is?
8x.
Yes. Technically, it's this, 4 times 2x, but we're not going to write that. We're going to go straight down to this. Exactly what Reese said, and said 8x. Good job. Josie, what do you think on 6?
Would it be 16x cubed plus 9x squared plus 4x plus 1?
Very nice. Good. Good job. And again, imagine if I'd asked you this question yesterday, the amount of work we'd have to do to get down to this derivative. And now we can just do it in one quick little heartbeat. Let's just talk about that last number there. This is a 1x to the power of 1. Excuse me. 1x to the power of 1. Okay, and if we follow the same rules, we bring the 1 down, and it's 1 times 1, x to the power of 0. Okay, 1 less. What is 1 less than, or what does x to the power of 0 mean? Well, x, any number to the power of 0 is 1. So this is just like 1 times 1, which is 1. Great. Jenna, how about 7?
Just equals 7.
That's right. And again, we can imagine this 2 ways. 7x is a line, pretty steep line, like that. And if we were evaluating all the derivatives at the different points, all of the slopes of the tangents, all of them would be 7. 7, 7, 7, 7, 7. And so the derivative is just 7 always. That's one way. And the other is what I just imagined. 7x is 7x to the power of 1. If we follow the rule, we bring that 1 down and multiply it by the front, which is 7x, and then 1 less than that is 0. And anything to the power of 0 is 1. And so that just ends up being 1, which means you're left with 7. Okay, so both a graphical representation of why this works and an algebraic representation of why the derivative is just 7. Great. So let's kick it up a notch. So I talked about that house analogy. Because we've built a great foundation and a great first floor, we can start doing second, third, and fourth, and fifth really quickly. You can build this skyscraper in a hurry once that good foundation is there. And so we've quickly graduated from simple polynomials that we've been studying the last couple of days into some more complicated questions. Now, before we go off and answer 8, I'm going to offer you one more suggestion for when we're differentiating. And that is to try and make your function as user-friendly before you differentiate. Okay, so if you've got something that looks a little nasty, like some of these, we want it to be user-friendly before we differentiate. So looking at in number 8, I've got y equals 3x all squared. Now, that means 3x times 3x. So before I differentiate, I'm going to say that this is actually 9x squared. Remember, when it's being squared, everything in the brackets has to get squared. Okay, so 3 squared and x squared. Or you can imagine this as 3x times 3x, right? When it's squared, now you can see it's 9x squared. So I haven't done any calculus yet. All I've done is made my original function a little user-friendly. Now I'm going to differentiate. So you see how I didn't put the y down there because I didn't change it. All right, I just changed the appearance, but I didn't do the calculus. Now I'm going to do the calculus. And Kennedy, what do you think the derivative of 9x squared is?
18x.
There you go. Oops. Not the square, just 18x. Perfect. So to help you with that, you're going to see that I'm going to do them in 2 different colors. Anytime I'm adjusting the question, I'll keep it in the same color as the question. And then you'll see my calculus happening in green. Okay, and for you, you want to make sure that you don't forget to tell me when you are differentiating. Okay, so make sure you tell me that's the line where I'm differentiating. That's when the calculus comes in. Okay. In this case, in 2, what I might imagine instead of this is that this can be rewritten as 1/3 w squared. Okay, so dividing by 3 is the same as taking 1/3, just like dividing by 2 is taking a half. So I'm going to rewrite it like that. Squaring something in brackets means that everything gets squared. So this is going to become 1/9 w squared. So just imagine that that's 1/3 w times 1/3 w. So a third times a third, 1 times 1 is 1, 3 times 3 is 9, and then w squared. And I still haven't done any calculus yet, but I think I'm ready to try. Cutter, you want to try this one?
Sure.
Yep.
So again, you would you have to simplify it. So you'd have to. Sorry, this is 10, right? Or is it 9?
I'm on 9. So
Okay.
I haven't actually done the calculus yet. I'm differentiating now.
Okay, so then you need to like multiply over. So you put the 2 on top. So it's 2 over 9 and
Yeah.
then W.
That's right. And technically it's W to the power of 1, but we wouldn't write that. Good. So I don't care if the coefficient is a fraction, it still gets multiplied, right? And Cutter did that exactly right. Good. So all the work actually happened in making it user-friendly, and then I differentiated. And again, I don't care if the letter is a Y or a V or whatever, we're still using the same notation. 10, I think already is user-friendly. Does someone want to take a stab at the derivative of 10 in 10?
What is the exponent? I can't really read it.
Yeah, that's fair. That's a 1/5. Okay, to the power of 1/5. So I'll do this one probably because it's a little hard to read that. But I don't care if the fraction or the exponent is a fraction or a number, the rule still applies. I'm going to take this exponent, bring it up front and multiply it. And so it becomes 15 times 1/5. I'll write that down. 15 times 1/5 is 15 over 5, x to the something. So I'm going to deal with the something in a second. 15 over 5 is just 3, x to the something. Now the something says that it is 1 less, right? So I got to do 1/5 minus 1. Well, 1, when we're dealing with fractions, is actually 5 over 5. And so if we're subtracting, it's 1/5 minus 5/5 is negative 4/5. That one's a little nasty. Definitely would have been nasty if we had to do it yesterday, trying to raise something to an exponent 1/5. I don't even know how to rainbow that, but it's fine. We can handle it here. A little bit more challenging because you're subtracting from a fraction. So I had to put it in common denominator, but we get that. We won't see 1/5 too often, but we will see another fraction that we'll get used to doing. And that's going to pop up in this question. So the root function. Remember yesterday I hinted at the fact that I used to take the derivative of the root function from first principles, and this year I decided we weren't going to do that. And that's because it is kind of nasty. So, and when I'm taking derivatives of root functions, I really don't have a rule on how to take the derivative of root functions. But I do have a way to take the derivative of exponents. And so I'm going to make this look a little more user-friendly by changing it into an exponent. The square root of x changes to what exponent?
Squared.
Sorry?
Is it squared? Or is
X squared is actually x squared. It's different.
A half.
A half, that's right. Okay, so let's remind ourselves of that. Remember, the square root turns into a half. If it was cubed root, it would be x to the 1/3. If it was fourth root, it's x to the 1/4. Okay, so remember that from we did a lot of that in grade 11. We did a little bit last course, but definitely a lot in grade 11. Okay, so we've actually changed this into x to the power of 1/2. Now I'm going to differentiate. Just like in the other ones, I'm going to bring the 1/2 down, 1/2 x, and now I'm going to subtract 1. So I'll do it once here. This is 1/2 subtract 1. Well, again, subtracting 1, I'm going to say is 2 over 2. I'm going to get a common denominator. And y prime then is 1/2 x to the negative 1/2. Okay? That is a little bit nastier than some of the other ones. So you can imagine why I decided to skip it out of that. Okay? I'm okay if you leave it like that. Some books will rewrite this. The negative exponent tells you take the reciprocal and put it on the bottom. And the 1/2 means square root. So you'll also see this as the same answer. Okay? The 1/2 part comes from 1/2. So this 1/2 part is the 1/2 part, okay? And then the 1/2 in the exponent tells me the square root, and the negative tells me to put it on the bottom. All right, so that's where all of that's coming from. But I'm fine if you leave it as that answer. Even rational functions. Now, yesterday we did do rational functions. We did do rational functions from first principles the long way. But we can use these differentiation laws and rules to do it much quicker. But before I try and use those rules, I want to make this look a little bit more user-friendly. And I do that by recognizing that this x is on the bottom of a fraction. I can move it to the top by using negative exponents. So I'll remind you again, you did a lot of this in grade 11. We did it a bunch last semester as well. But when you have x to the -4, the negative tells you to make a reciprocal and put it on the bottom, x to the power 4. X to the -7 then would be 1/x to the power of 7. Okay, so that negative exponent tells you to put it on the bottom. So I just work backwards, and if it's on the bottom, I bring it up to put it on the top, but with a negative exponent. I haven't done any calculus yet. I've just made it more useful. Now we can apply the calculus rules, and it's much easier. Kelsey, you want to try this one?
Not really, but sure. Would it be 12x to the power of -3?
Almost. I love your 12. What's 1 less than -4?
-5.
Yeah, a little tricky there, right? Because I would have guessed 3 as well, because if it's 4, it's 1 less is 3. But when it's -4, 1 less is actually -5. What I do love is Kelsey recognized that she brought the -4 down and got multiplied by the -3, so saw it was +12. So good job on that. All right. Good, we're doing great. I'm just going to keep going. This first lesson's a little bit longer, but the second one is not as long. So I'll just finish this first lesson and give you a break. So we're going to start to, because we can differentiate now a lot quicker, we can tackle more complicated questions, or we can start to use the derivative to imagine some somewhat real life situations. So think back to the first calculus question we looked at was the dragster, and it had a function. That one was 19t squared. And we differentiated that, believe it or not. We took the derivative. It took us a while, but we found the slopes of the secants and then the tangents. And then we got the derivative represented the speed or velocity. So the derivative or the steepness of that curve was the speed or the velocity. That curve could have been any function, including this one. So this one is a position function of some moving object. This calculus here actually happens a lot in particles moving through a wire, talking about the position of the particles as they move through it. And we all know about the speed of things coming through. Okay, so if you're using the internet, of course, you're getting particles going through the wires and electrons going through the wires. So it gets modeled with some sort of model. Now, the real life modeling is much more complicated than the function I'm using, but it can still talk about where the particle is, where the electron is, and where it is will tell us how fast it is. So if we can see how fast the distance is changing, we know how the speed is. And of course, the bigger the speed, the better the connection, the better the internet, the blah, blah, blah. All right. So in this case, our function first looks a little bit more complicated because it's a big thing in brackets being squared. So my advice was, before you start differentiating, which is what we're asked to do here, remember this notation is the third type of notation for derivatives, okay? What we want to do is make our question look as easy as possible. So I'm actually going to rainbow this function. 4 plus 3t squared is 4 plus 3t times 4 plus 3t. So I'm going to rainbow it, make it a little bit more user-friendly. So this is 16 plus 12t plus 12t plus 9t squared. And so 16 plus 24t plus 9t squared. So I have made my position function into a trinomial. And this I can differentiate much easier than what I started with. So again, I'm staying in blue because I haven't done the calculus yet, but now I'm going to do it here. Now I could have said S prime, that's one notation, but this is the other notation, ds by dt. Oh, I just saw a hand up yet, Kelsey?
Is it supposed to be 24t or 24t squared?
Oh, thank you. I don't know where I wrote that down. Thank you. Yeah, 24t for sure. Thanks. Let's see here. Aaron, you want to try and differentiate this one?
Sure.
Okay.
Would the 16 just stay a 16, or does it become 1?
Well, you tell me, what's the derivative of a constant?
I'm not sure.
That's okay. Let's go back here. The derivative of a constant is?
Oh, 0?
Yes, good. So the derivative of 16, it's not going to stay 16, it goes to a 0. So I won't even write it down. Okay, good. What's next?
And then the 24 without the t?
Yep.
And then 18 plus 18t?
Yes, perfect. Good job. Yeah, so just don't forget those constants are just the derivative of those are zeros. 24t is just 24. And then, of course, we're using our power rule. 9 times 2 is 18t. Great. So we found this, which is the new function that's describing speed. So then, or velocity. And if I wanted to know how fast it's going or what the velocity was at a specific t 3 seconds, which formula would I plug it into? The green one or the blue one?
The green one?
Yeah. Because the green one is talking about velocity, the blue one is talking about distance. And I want to know the velocity. And so I just plug it in. 18 times 3 is 54. Equals 78. And this is in meters per second. All right, good. So being able to differentiate really quickly allows us to go off and tackle some other questions. And then we've got one last one before we go to break. All right, so this question here, I'm going to ask you every unit for the rest of the course. Find the equation of the tangent to the curve. So yesterday's, or was it yesterday's classic calculus question or 2 days ago, I can't remember, that said find the slope of the tangent. I think it was yesterday. Find the slope of the tangent, which is really valuable. Here we're going to go a step further and find the equation. Now, our equations are going to go back to grade 9, not the equations that we studied in vectors. Don't think of those. Think of back to our grade 9 equations, y equals mx plus b. So the two things I need to find the equation of this tangent is the slope of the tangent and the y-intercept. So the slope of the tangent is the calculus that's going on. So I've got this function here, and I want to know the slope of the tangent at the point -1, 7. So of course, if I want to find the slope, I need to differentiate. So I got my function here, but I want to know y prime. Mia, what is the derivative of 2x cubed minus 5?
That's 6x squared, and the -5 just disappears.
It disappears, exactly. Great. So this is the derivative. This describes an equation for all of the different slopes of the tangents. I only want one of them. I want the one that happens right here. And in particular, I'm going to use the x value from this. So the slope becomes 6x squared, and this x is -1. So be careful to remember bedmass. We're going to exponents first. So -1 squared is just 1. So 6 times 1 is 6. So the slope of our tangent at this point is 6. You'll notice I've moved from the derivative notation here, which describes all of the slopes, to the single slope that I've been asked for in this question. And I know that the slope then is 6. So far, I have most of my equation for my line. Remember, equations of lines are written in y equals mx plus b. And I just figured out the slope. Does everyone remember back to grade 9 to how I then found my y-intercept?
Sub in the point.
Yep, sub in the point. So we're going to take this and sub it in. So now I get to use that y value. The y value was -7. The x value was -1. And I figure out the b value. So -7 equals -6 plus b. Add 6 to both sides, and I get -1 equals b. And therefore, the equation of the tangent is y equals 6x minus 1. Just as a heads up, your textbook likes to write the answers in standard form. I don't care. I like this answer, but they will write the answer in standard form and have it written like this. They'll probably have the 0 on the other side, okay, but they're just putting it in standard form. I don't care. I am totally pleased with that. But when you're checking your answers in the back of the book, you'll want to make sure you have that. All right, great job. So we did a lot of differentiation here on our first lesson, and I'm going to make sure to give you a break and a little bit of time to do some practice. You won't have enough time to do all the practice now, but you're going to have some practice throughout the day. So we're not doing that. We are going to do page 138. What we are going to do Now, when you go to number 2, you're going to see there's lots of ones there, but a lot of them are one-line answers. Okay, so like the derivative of, a lot of them are things like this. Y equals 7x squared. What's the derivative? 14x. That's an awful one. 14x, right? So they're going to be quick and painless type ones. So what we're going to do now, this was the long lesson today. Our other 2 lessons we're doing today are shorter, much shorter. And after each lesson, you'll have some time to practice. So I'm going to give you, the reason we're taking the extra time to practice here is because if I start moving on without you practicing, the skyscraper is going to get a little wobbly. So we want to take the time. So I'm going to give you a break now and some practice time, and we're going to come back together at 10:30. Okay? And then at 10:30, we'll do a short lesson in which we should be able to finish up before lunch. Okay? So if you have any questions, you can stay on. Otherwise, I'll see you at 10:30.
I had a question.
You bet.
It's not about this, but it's about the limits assignment.
Okay, just 1 second. I'm going to stop recording, okay?
Okay.